Coming this week, Shaoyun will spec Gromov-Witten Invariants and complex.
Great. Thank you for the introduction and thanks for the invitation. It's great back to be here. Okay, so that's my title, and the talk has 3 parts. So in the first part, I'm going to introduce some background, and it's most about topology in the 50s. And in the second part, I'm going to state the results, especially why it's relevant for symplectic topology. And in the third part, I'm going to discuss a little bit about the methods which are used in establishing the results. Okay, so let me get started. So we have 2 objects to consider in this talk, Gromov invariants and complex Cobordism. So I start with the second one. So suppose we have a closed smooth manifold. So what is a stable complex structure? So we consider tangent bundle, the manifold M, and we consider the direct sum of this guy with a trivial bundle, say of rank R, rank K, and a stable complex structure, then a almost complex structure on this bundle. So it's J, property that J squared is equal to minus identity. Okay, so stable refers to this part. You have to take direct sum with the bundle, trivial vector bundle, and complex refers to the existence of such a J. Okay. And using this, say, manifolds, we can define some kind of homology theory, non-convex Cobordism theory, and we introduce a notation for that. So here I'm trying to describe this homology theory subject to this homological space, which is given a single point. So what is that? It's going to be the free abelian group generated by, say, all possible closed stably complex manifolds. So I'm stably complex. And this kind of summation for this group structure comes from disjoint union. So I'll just write plus comes from disjoint union. And we should model out some kind of equivalence relation. And this equivalence relation comes from Cobordism. So we say these 2 manifolds are subordinate to each other. In other words, this kind of stable complex structure means the following. Means we can find a manifold with boundary is given by disjoint union, these 2 manifolds. Of course, there might be some non-trivial topology here, and we want that the stable complex structures are compatible. In the sense that the restriction of the tangent bundle of this total space is given by, on the boundary can be written as direct sum of the tangent bundle of the boundary with the trivial line bundle. And we want some suitable compatibility of these stable complex structures. So this is a relation I introduced over here, and this defines this group, the complex Cobordism group. Any questions so far? All right, so here's a theorem due to Tom. And for the part concerning torsion, it's due to, I guess, Milner, which says the following. One can compute this abelian group. So it's isomorphic to such a ring. So here, these variables C1, C2, C3, they are of even degrees. So the degree Ci is equal to 2i, and you should think of them as, say, term classes. And I forgot to say that over here, there is a ring structure coming from addition product. And here is a polynomial ring generated by counting many variables. And there's also a ring structure. And this isomorphism is compatible with the ring structure. So that's the calculation. And given this kind of geometric definition of complex cobordism, it's kind of hard to imagine how can one really make such computation possible. And so the crucial construction for proving this statement is the following, the so-called Hungarian-Tom construction. So roughly speaking, it says that, to understand this geometrically defined cobordism theory, one can instead look at some kind of collection of spaces, more or less coming from, say, classifying space of complex vector bundles, and consider their homotopy groups. On that spectrum called complex cobordism spectrum. So I won't define what they are, but it can be very concrete. And this mu more or less comes from the Tom space or fiberwise 1-point compactification of the topological bundle over the classifying space of complex vector bundles. Okay, so this is a classifying space, classifying, say, complex vector bundles of rank K, and over there lives this tautological bundle, the universal bundle. And we can do this fiberwise 1-point compactification. So each fiber, originally they're Euclidean spaces, but they become spheres. And we can try to go from these spaces to understand as cobordism. So, of course, on establishing such an equivalence requires some argument, but let me just comment on one important aspect which is relevant for this talk. So I said here, we should understand homotopy groups of such spaces or such spectra. It means that we should look at, say, homotopy classes of maps from, say, manifolds or special spheres to such a space. Calculate homotopy group you need to understand say maps from spheres to Tom space. Okay, so I'm drawing the diagram in a very strange way, and you'll see why. So the thing we care about should be this kind of F1 map, but because we have this projection map from the topological bundle to this classifying space, we also get a map from our sphere to the classifying space of complex vector bundles. So let me write it as F2. So you could ask, what kind of data is this? So the point is the following. So in this picture, we see that in this diagram, F2, that specifies a vector bundle over the sphere. A complex bundle of rank K by E over the sphere, because by definition, BOK is classifying space of such objects. On the other hand, we have a lift of F2, which is F1. It means that we have a section of this vector bundle. Okay. So that's the picture we get. And to go from such a triple to, say, stably complex manifolds, what we have to use is Thom's transversality theorem. And by transversality, let's go back to this triple. For this section S generic, we can infer that the zero locus is a smooth manifold. Moreover, the sphere has a standard stable complex structure because there's this Euler sequence, and vector bundle E is also complex, implies that this guy here is actually stably complex. Okay. So that's the explanation of how to go from, say, homotopy groups of these spaces to, say, stably complex manifolds. So the crucial thing to think about is from this data, we can get such a triple, namely a manifold, a vector bundle with a section. Then by transversality, we can perturb our section so that their locus is smooth. So it's a manifold. Okay, any questions so far? All right. So now we can ask, what if we put group actions everywhere? So still, I want to go from some kind of group calculation to manifolds, and let's see what could go wrong. So there's a, so let's maybe for now fix a compact Lie group. For compact Lie groups, there is of course, a well-defined theory of classifying spaces of equivalent vector bundles. And over such a space, there is this universal vector bundle, logical bundle. That's also fine. So now let's say we have some kind of equivariant map from some kind of sphere with a G action. And we can just repeat diagram just for over there. So this still gives us such a triple. So our ambient space, the sphere, has a D group action. Our vector bundle is equivariant in this group action, and our section is also equivariant. But now we want to go back to say generally manifold, say, because the previous lesson taught us that we want to really go from such a homotopy object to some geometric object, maybe manifolds. We have to do that here as well, but the crucial thing in the previous setting is the transversality, which fails in this case with group action in general. A very simple example is the following. So if you consider the real line, you can look up, of course, more complicated examples. The real line, the domain here, the Z2 action is trivial. Suppose that we consider Z2 equivariant maps from this real line to the real line, but we involve non-trivial Z2 actions of some. You see that the only equivariant map is a constant map, it's a trivial map, and it doesn't satisfy transversality. And that's the typical example of failure of transversality in the context of group actions. Okay. So maybe this is what this kind of analysis can give us the most. And I would say this can be viewed as the topological origin there are different languages of saying the same thing, or slightly different things. You can see it's Cornish structure. Or even dimensional incarnation, polyfolds. Okay, it's just that we want to achieve some kind of transversality from some motivation, but we realize that because of the presence of group action, we cannot do that. So instead of, well, of course, you can try to see whether there's some other way to achieve some versions of transversality in order to make this comparison work. But maybe the canonical thing to do is to just keep all the structures you get there. Namely, you remember this space over there on the sphere, also remember this kind of vector bundle over that. Together, you endow that with a section. Okay. And so now let me try to introduce different object. So this blackboard, I introduced this group of complex cobordism, say complex manifolds, stability complex manifolds up to cobordism. And now I want to incorporate group actions.
So you're saying in this generalization, you no longer get any connection to cobordism as in the theorem?
That will be one of the theorems I will state later. And so, but for your question, there are different answers. Is that you want some kind of geometric description of, say, homotopy groups of such vector spaces, okay? And instead of trying to achieve some kind of transversality, you can just keep the sections here. So you consider cobordism theory of objects, which are like a manifold, a vector bundle together with a section.
Oh, okay.
Okay. And then you can just try to do the same kind of conjective construction, in the end, they do match.
So it should be possible, rather than doing this finite dimension stuff, to have sections of photon bundles.
That's
Infinite dimension photon theory.
Mhm.
And then I think there should be a sort of an equivalent picture of this. Yeah?
I think so. Yeah, that's something I'm going to state.
And then, of course, the stable convex has to be built into the photon theory.
That's right. That's right. So now I'm going to introduce a new gadget, which is a slight variant of this complex Cobordism group. So in that discussion, I talked about the V group acting on spaces, but we can also consider, say, orbifolds, which are like quotients of V group actions with finite stabilizers. So here's the notation for that. So this is called the Cobordism group. So-called derived orbifolds. It's a strange notation. Let me just try to make what I just said more precise. So for this Cobordism group, the objects are the following form. So D is a smooth orbifold. And E is a orbifold vector bundle. And S is a section. So locally modeled on equivariant sections. And we require that the zero locus of the section is compact. And for the analog of stable compact structure, we require that so the tangent bundle is stable complex, and this vector bundle E, usually called the Gaussian bundle, is also a complex vector bundle. Okay. So we consider not only manifolds, but manifolds with vector bundles together with a section, and they are like elements in this Cobordism group. And to define some kind of theory as this, we need to model out some kind of equivalence relation generated by Cobordism or related objects. So, and then this guy is defined by modeling out Cobordism. And some other relations. And for Cobordism, it's more or less the same as the previous picture. Have a manifold with boundary, or here in this setting, orbifold with boundary. So here we have our D prime, or D twiddle. The boundary is given by the disjunct union. Over each part, there are
A question for the just technical. For the orbifolds, you assume something about the singularities effective or something, or is that not necessary?
So I can introduce another equivalence relation here in other part, which is a stabilization relation. We can thicken up the orbifold by replacing that total space of vector bundle, and also replace the bundle here by the direct sum of this bundle with the pullback of that bundle. If I introduce that, it doesn't matter if our sigma is effective or not. Yeah, because every orbifold is equivalent to every direct orbifold is equivalent to an effective one. This picture, I'm trying to describe Cobordism relation. It's just that, except for the coordinate between the orbifolds, there should also be vector bundles extending the vector bundles on the boundary, and also sections on the boundary. And so this for Cobordism. and some other relations. So I'll be sketchy here. For example, we could replace the orbital D by some kind of neighborhood. A neighborhood, the zero locus. And also replace the vector bundle by the restriction to this open neighborhood, replace the section by the restriction as well. The point is that we more or less just care about the behavior of this structure near the zero locus, so we can do that multiplication. And also there is this kind of also stabilization relation, which amounts to, say, replacing B by total space some other vector bundle over that I and replace our vector bundle by the sum of these two bundles, our section by pull back this section plus the tautological section of this vector bundle, and you can check that this kind of move doesn't really change the behavior of the zero locus. Okay.
Is that condition on the section?
Section. So it's an orbifold. So in terms of orbifold charts, they have to be equivariant. Okay. On the other hand, we don't really require that to be smooth. It can be, say, a continuous section, but I require the zero locus is compact.
You said you're not required, but you said you're required to be smooth or not?
I don't require that to be smooth.
So it's
But for developing the theory, I mean,
yeah, so you define an algebraic theory if you take the smooth ones, presumably the same theory.
that's the same theory.
But the space of sections is connected?
But if the section is connected, doesn't have to be. I can take this from the union.
Oh, well, okay, this, what did you know?
Space of sections or the base
The space of sections.
Base of the section.
Yeah.
Base, you mean the D here?
No, the space of all sections.
Space of all sections.
Yes. Oh,
What do you mean by it's connected or not? It's not part of definition. I mean, it can be a proposition, but
well, I mean, if the space of all sections is connected, then
it doesn't matter.
I'm having trouble understanding why you have to specify.
I mean, the
Well,
D
yes,
here,
part of the-
D is not compact. D is not compact. I don't require that to be compact.
In a section that the solution space is compact.
It may not, because at
If
the top, if it's uncompact, the behavior of near infinity may have like topological instruction to connect different sections.
Okay, I guess the point I want to emphasize here is I don't require D to be compact. I only require zero locus to be compact.
Okay.
Okay.
I see. So it's kind of, okay.
Okay. Okay, so this can be viewed as a model for defining this group. And of course, as I mentioned earlier, one could try to, I mean, I'm not an expert on polyfolds, but I can speculation. There is a different model of this Cobordism group defined using polyfolds.
No, I mean, you can take this job union of photon situations, monarchs,
Yeah,
and if it's. Yeah, so I think you can do all this stuff.
right. And yeah, and to relate this, maybe the approach and the previous approach, there is some kind of dimensional reduction in between.
Yeah,
But that
yeah, I
goes
think, it would sort of somewhat fattened out, and that would give you this kind of stuff.
Yeah, that's
right. Or this you could sort of, if you want to make it infinite dimension, do some trivial stuff, it becomes infinite dimensional, but
Right.
the solution senses.
Yeah, that's right. Right. Okay. All right. So far it's about some sort of elementary algebraic topology, which are supposed to be developed maybe back in the 60s or 50s And then let me move to the second part of this talk.
So can I ask a question to Helmut? Helmut, so this the polyfold. Helmut,
Yeah. Just a
Uh,
moment, okay.
so in the polyfold picture, so when you regularize, you get a manifold. Okay, well,
Well, I mean, regularizing, yeah, so you can always regularize those ratios, but then you get this branched business. But you could sort of thicken it up and have the section and don't take the zeros. You construct a finite dimensional thing,
right.
which is, if you sort of expand it, would be sort of isomorphic to the polyfold situation, you have finite dimensional things, and that is a section picture with a compact space.
And you see some kind of stable complex structure there also in that picture.
Well, this he put it as an assumption. You have to give, so he assumes that they are stably complex, so you have to put that in.
But I mean, in your picture, do you?
Yeah, you can, I think you can formalize that too.
Okay.
Yeah, it's just like there's a model for understanding the spectrum of representing complex K theory in terms of quantum operators. You can put as a part of the structure in a set of polyfolds, and it's easy to see there. Okay. All right. So why is it relevant for symplectic topology? Of course, for experts, it's obvious, but let me explain that. So, okay, there are many variants of the theory, but let's consider the most basic one. The modular space of stable maps to closed manifold. So there's some modular space. Let me recall the definition here. X omega is a, say, closed symplectic manifold, and J is a almost complete structure, say, named by omega, and G and K, they're a pair of non-negative integers, and A is a homology class of target space, and this space here describes, say, maps on surfaces, the manifold which solves the continuum equation, and the homology class represented by this map is given by A, and the genus of this surface is G, it's K marked false. So that's some modular space relevant for some topology, modular space of pseudo-modular curves with some logical data prescribed. And so there is a heuristic which says that the Cobordism class of such an object is an invariant, is a symplectic invariant. Particular independent of the J. By considering, say, cobordisms of modular space. And to make this heuristic more precise, so precisely, the statement should be such modular space gives rise to a well-defined class in this cobordism group. Okay, so there are different ways of proving this. Yeah.
So which means that there is a section of something and that class is an element there. That is what it means.
That's right.
Yeah, so I think from the glory point of view, is you write down a Prism problem, then you put a bracket around it, and that's your class.
That's right. Exactly. Yeah, as I said, there are different ways of realizing this.
Yeah.
Via this partial approach, that's one. And via finite reduction approaches, I mean, there's different ways of realizing this. Okay, so that's the relevance. These modular spaces, so maps, naturally give rise to classes in this Cobordism group of derived orbifolds. Okay, and the point it lies in this group is that so there's some features. So firstly, you have to sort of keep a section there. That's because the del R operator from section does not really intersect the the zero section transversely in general. So that's closely related to the picture we discussed over here. That's because the elements in this modular space come with automorphism groups. So you have non-trivial automorphism, and it's like the analog of this five-dimensional picture. And then realize that if you want to perturb your del R section to make it transverse, there's some obstruction. You cannot do that. That's why instead of getting, say, an element inside the original complex cobordism group, we only get a version in this kind of derived or this kind of triple from these modular spaces. Okay. All right. So, but here's the question. I think many people have asked this. Yeah, for example, I think Tantsevich has some strange speculation in his paper, counting rational curves inside the algebraic varieties. Yeah, in that paper, he does a lot of things, including formulating Gromov-Witten kind of axioms, also about proposing virtual localization. And there's also a sentence in his paper which asks, okay, how can we redefine a class inside complex cobordism? Now this direct version. Okay. So of course, this derived version is kind of canonical because in some sense, especially using this kind of polyphos point of view, you don't have to make any choice in some sense. That's maybe the universal invariant. But the issue is that we basically know nothing about this guy over here. We want to get some more concrete understanding, so we try something more. And non-reducing theorem. And as I say, it's in progress. And I'm going to be with Muhammad Abouzaid. This B is not Blomberg, so. All right, so it says the following. On the inclusion from where to where? Well, from complex cobordism to this derived version. So this map, so we take say a manifold here. We can just map to this kind of triple where the bundle is a rank 0 bundle and the section is a trivial section. There's like inclusion here. Inclusion splits. bit injection. Okay, so in other words, it means that we can find map in the reverse direction. I call this iota. It says that the composition this order is the identity. And there's an immediate corollary which answers this question. If we apply this kind of splitting map to this Cobordism class, this can be viewed as a complex Cobordism value Gromov. Okay. So it's really a result of algebraic topology that we can split off the original copy of the complex Cobordism inside this version. So this result is already non-trivial, even in the equivariant setting. What does it say? It says that, so at the beginning I talked about equivariant Cobordisms. So there's kind of equivariant complex Cobordism. And there is an inclusion which geometrically corresponds to, say, sending a manifold the manifold cross with the lead group. So it says that this splits. Okay, we can just restrict ourselves to possible orbifolds so that all the stabilizers, some groups of this given group gamma, and it's compatible with transfers. Because for an orbifold to exist, what you have to do is you have locally this kind of equivariant picture, and you're able to patch these kind of local pictures together, which means that you have to go from one group to the other that corresponds to transfer. So in terms of this equivariant Cobordism language, it says that there exists a splitting map so that if you change the groups, things are sort of compatible. Okay, any question about the statement?
I have forgotten what is mu gamma.
So mu is like complex Cobordism, right? So gamma is finite group. So this is like equivariant version of complex Cobordism.
So you described this right in the beginning, right?
Yes. Yeah. Yeah. Just think instead of
So you just have a gamma action on the.
yeah, it's gamma action on everywhere. Instead of being an orbifold, it's a gamma manifold, gamma vector bundle from the current section.
Is this map as canonical?
What do you mean by canonical?
Natural.
Yeah.
Yeah.
The third
Yeah.
one.
So this splitting is actually splitting of multi theories. And so, you know, one thing to say is the following. For some classes of finite groups, for example, gamma B and Z mod 2 or something, algebraic topologists can calculate this equivariant Cobordism very explicitly. And based on this explicit presentation using generators, there are many splittings you can write down, right? So in other words, claiming a splitting is canonical it is always too much. And I think the point here is that there exists one.
Maybe my question should be, can you describe it? Or
Yeah, of course. Yeah, that's the point of the construction.
so there's an abstract splitting that you get from.
It's not based on homotopy theory. It's based on geometric arguments. Any other questions? Okay. Another thing to say is that this complex cobordism is the so-called universal complex oriented commodity theory. You can go from this commodity theory to various commodity theories, including, rather for topologists, Morava K theories, or maybe more classically K theory or ethical homology. They can all be be specialized from complex cobordism. So given such an invariant, we get invariant in all complex oriented commodity theories. Okay. And there's a concrete application of this. So, well, maybe it's not concrete depending on your taste. So the sweep out map. So I'm going to do so here let X omega be a compact, the closed symplectic manifold. And we consider the space of loops of the Hamiltonian diffeomorphism group.
Before we continue, so what's the relation with the work which you did with Q?
It's like a refinement of the previous work.
It's this invariant is a refinement of that.
Yes. I mean, there are places where we use a different notion of transversality in this setting, but everything should be different in co-dimension 2. So at least when it's specialized to Z, it should have our previous invariant. Okay, go back to this theorem. So we consider the space of loops, base loops, based on identity in a space of Hamiltonian diffeomorphisms of our simple manifold X omega. So there's some algebraic topology operations. You can do a one-point compactification. You do a smash product with a circle. So this guy defines a sweep-out map to the automorphism group of X. I'll explain what I mean later. And if you smash that with mu, this is not homotopy. To be more precise, so suppose that we have a loop of Hamiltonian diffeomorphisms, and suppose that given the angle inside the circle, then the evaluation map here acts on space X as a diffeomorphism, and you can do it in a more homotopical fashion. Instead of looking at the space X, you look at the corresponding infinite suspension. So in other words, we just care about the stable homotopy of this space. Then it says that this action becomes trivial once you smash this space with complex cobordism. So in other words, if you don't look at things as refined as stable homotopy group, but if you just look at complex cobordism groups, this map is sort of trivial.
So could you say a bit more what you mean by the action is trivial? So for each state that you have non-homomorphism.
That's right.
And then for the loop, you have,
So I mean, just consider this as addition product. Forget the MU here. So the evaluation defines a map from this product to the space of, say, diffeomorphism groups of your manifold.
right?
Instead of considering, say, diffeomorphism groups, we consider its automorphism group and replace X instead of being a manifold by its stable homotopy type.
Well, that's somehow that's that plus thing.
Plus is one-point compactification.
Oh, plus one, okay.
Right.
Right, that's very strange because we know, of course, that if you don't smash with MU,
Mhm.
then the map is non-trivial.
That's right.
Well, at least without the plus. I don't really understand the plus, but
I mean, plus is just a way of formulating, say, analog addition products in this stable homotopy category.
all right, you just because you want to have a smash product.
Right. The point is about taking the smash product with MU.
Interesting.
Right. I think you know this pretty well because this can be translated into a family version of homological splitting result.
Family version of what?
Homological splitting result. Vibration over S2 with clutching map given by Hamiltonian circle. And over MU, this homology splits. Say total space, consider this homology is going to be a tensor product of the homology of S2 with the homology of the fiber. We can consider family version, family of loops parameterizing. So this is a universal family parameterizing such loops, such vibrations. They also split. Okay. All right. So in the last part of this talk, let me try to give you an idea of what really enters the construction. So the question you could ask yourself is the following. So how far is our homologized space your locus section of orbifold is that away from a smooth map? Okay, so because elements in the complex Cobordism group are represented by smooth, stably complex manifolds, and we start with some kind of strange gadget, and we want to ask ourselves how far is that away from being a smooth manifold. So at least there are three things to keep in mind. So although I said before that I don't really require the section to be smooth to set up a theory, so let's pretend it's smooth and illustrate the phenomenon here. So the first issue is that as or its continuous function, so we have no control of the zero locus. Even if we ask us to be smooth. I mean, take a smooth function, arbitrary smooth function, look at this pre-image parameter of zero, we have no control of what they are if the zero is not a regular value. And the second issue is, okay, suppose that we're, for example, in the algebraic category, and or maybe more generally, complex analytic category. We're lucky enough to make sure that S is complex analytic. There's still some issue. So even if S is complex analytic, because as we've seen before, equivariant transversality can fail. So the zero locus may have singularities. Although it's slightly better than previous situation because there are like algebraic singularity or complex analytic singularities. And thirdly, even if this X can be chosen to be transverse to the zero section, we only end up getting an orbifold. For general orbifold, if we take its core space or quotient space, it's not really a manifold in general. Okay, so there's some alterations, and they account for the non-smoothness of this space. And the point of this statement is to resolve all these issues. So let's go here. Let me just write it down how to sketch how to resolve these issues. The first issue that's based on joint work with Humboldt is before. So we can use complex polynomial like perturbations. We call no puncture perturbation. To make sure that the zero locus, I mean,
So is that very special for this kind of spaces, or is there a more general theory? Because that's abstract, so you could
It's-
ask,
it's a
it's
general.
on that level.
Yes. So for this part, we use some polynomial-like perturbations. We take advantage of the existence of complex structures to redefine these notions to make sure that if we consider so to get perturbation in the original section, so that if we consider the associatively free part of the zero locus, and this exposure, it only has algebraic-like singularities. They are not really algebraic, but there's a way of making them algebraic. Okay, at least by turning on some interesting class of perturbations, we can try to make the singularities more under control. The second part, okay, so now we are in this kind of nice world of complex analytic or algebraic singularities. So of course, there's a theory of resolution singularities that one can try to use. For the second part, apply not Hironaka's version, different version. Pretty important here, functorial resolution singularities. And this I'm referring to the recent work of Gromov-Witten, Temkin, and the Polish guy, a famous mathematician that I can never pronounce his name right. I think also cannot spell it right. Okay, something like this. So they have a paper.
Functorial means what in the derived, what does it mean?
You mean functorial or?
Yeah, functorial resolution of singularity.
It means that, for example, if I want to do perturbations in orbifolds, we do it in one chart, we have to go to another chart. That involves, say, finding a different information chart, which corresponds to a different group, which in a quotient presentation. So functorial, at least, is needed to really say go from one group to another. And to be more precise, it's like, so their result is really kind of easy to explain. So they do this so-called embedded resolution of singularities. So instead of considering an abstract algebraic space, they consider an algebraic space which is embedded in a smooth variety. So this is something singular we want to resolve. This is something smooth that sits inside. Functoriality means that if we consider a morphism in this category, in the sense that we have another smooth variety with possibly a singular subscheme, and so that this diagram is Cartesian. So X total is a fiber product, and this is smooth submersion. Then one can guarantee that the resolution of X twiddle inside Y twiddle can be pulled back from the resolution of X inside Y.
And is a resolution.
It is resolution. So their algorithm is like producing the resolution for such a pair. And the property of being functorial is that this resolution given by the algorithm can be obtained by pulling back the output here. This is very crucial for making whatever local resolutions compatible with each other. And for the last part, so suppose we have an orbifold, but it's orbifold, the quotient space, the core space, may be a singular space. How can we make it a smooth manifold? So it's sort of inspired by functorial de-stackification in algebraic geometry. But in reality, we can just do everything in almost complex world. Point is the following: it has two steps. The first step is given an orbifold, let's say it's almost complex. One can do a sequence of blowups so that all the stabilizers are abelian. So that's the first step. This step allows us to more or less reduce the singularities to toric models. In the second step, there is a way of trying to make these local characters independent. So one example is the following. Let's consider the following two-dimensional complex orbifold. So consider the one-dimensional complex of vector space, which is acted on by the group Z02. And the -1 here refers to the sign representation. Then if you consider this quotient, this guy is now smooth. Okay, so that's a typical example of ordinary double point singularity surfaces. However, if now, instead of considering this direct sum, we consider direct sum of trivial representation, the sign representation. So the Z-mod 2 group actually only acts on the second factor. The quotient space is still this kind of smooth complex line. That's smooth. Okay, so in other words, in the abelian situation, if you could somehow make these characters independent in suitable sense, we can make sure that the quotient space is actually a smooth manifold. And there is a way of doing this. And combining these two things together, I can make sure that, okay, this is also realized by blow up. So you can make sure that function space of this blow up is smooth. And of course, there's a final point to say, if your input is a manifold, everything here does nothing to that. So that's why this inclusion map splits. So I'll stop here. Thank you.
Any questions?
So you just described the construction of S.
I want to ask about the notation of this
Okay,
omega,
sure. Omega. Okay,
like this, yeah. What is the U? What is the point?
right. So U stands for unitary. So that's the structure group of your tangent bundle if you choose a metric. And PT, I mean, it means that I'm looking at this multi-theory over a point. So you can replace this point by the topological space in general. So instead of considering cobordisms, I mean, in a traditional sense, you also endow that with a continuous map to topological space. And that defines multi-theory of a topological space. So for this talk, I just restrict the case where target is a single point.
Oh,
And D here stands for derived.
yeah, there. Any more questions? If not, let's reshare again.
So MU has like some universal elliptic property, right?
What do you mean by that?
Well, it's like the universal elliptic homology,
It's universal complex oriented commodity theory.
complex oriented.
Elliptic homology is a special class of complex oriented commodity theory.
But it has some universality. I mean,
Yeah.
it's like
Right. Every complex oriented commodity theory can be specialized from MU. In other words, you can recover K theory, you can recover, say, Marat K theory, you can recover elliptic homology out from MU.
right. So and the derived version.
That's not enough.
Sorry.
I'm going to ask, is that also the inverse version for anything?
Yes.
That's not so clear. Because there's no, I mean.
So if it was universal, then you could just say that they, might even be the same thing. They might be the same homology theory.
That's just wrong. Because you can just take a point, consider a representation over the point, which is non-trivial on the group action. That's something that has negative virtual dimension.
I see. Okay. Right. So something different.
It's completely different, and no one really knows how to calculate this group.
Nobody knows to do what?
How to calculate this group.
Ah, okay, yeah. I believe that.
Okay.